Right. So where we had stopped was towards the end of this Carnot cycle. So what one had come up with is that we established that of all engines working between temperatures T1 and T2, Carnot engine was where it's reversible, and therefore the Carnot engine, because of its reversible property, was most efficient. The efficiency determined only by the, it is independent of the substance, and we haven't yet shown the most efficient part. That will have to come. We showed that the Carnot engine reversible is independent of the efficiency, is independent of working substance, determined by only the temperature of the two baths, T1 and T2. And we will have to also establish, which we haven't yet, that it is the most efficient, the reversible engine is the most efficient engine running between two given temperatures, T1 and T2. But where we were was that we had to get the, having said that the Carnot engine efficiency is independent of the working substance, we could take the liberty of calculating the efficiency with the help of the ideal gas. So that was our, that was where we were. And the engine is expansion when followed by another expansion, this one isothermal at temperature T1, and when it takes in a certain amount of heat Q1, and then the adiabatic expansion, where the temperature changes from T1 to T2 over here, and then isothermal compression to, so this 1, 2, 3, 4, the 4 stages in this process. From step 1, an isothermal expansion takes you here, and then an adiabatic expansion. So this is the adiabatic part, and then a compression stroke, which takes you here to 0.4, and then an adiabatic expansion to take you back where you belong. So that's the cycle, on all of it done slowly enough so that every, it's a reversible cycle. And this business of efficiency, which is now 1 minus whatever heat is given out, Q2 divided by Q1, because it comes from the work done by the amount of divided by the amount of heat taken in, takes in this amount of heat, can't convert all of it to work according to the second law, and therefore the work done is less than Q1. The efficiency is less than unity and determined by how much heat has to be rejected by the system. And so it is 1 minus Q2 over Q1. It is W. W is Q1 minus Q2, the total work done over the cycle. And
someone is waiting. Can you let him in?
Oh, yeah. So what we were in the process of finishing up was to show that this Q2 over Q1 is simply T2 over T1, and we had written down this question of the amount of heat which this is the isothermal process over here, where the amount of heat taken in Q1, the isothermal process is a question of integrate the no change in temperature. So delta U is equal to 0. So it is all integral PDV, and it is from V1 to V2, and it is RT1 and divided by V times dV, which is RT1 log of V2 over V1. And then there was Q2, which is the heat given out, which whose magnitude is V4 to V3, and it is RT2 over V dV, which is equal to RT2 log of V, which is the bigger V3, so by V4. So that's the amount of heat taken in over here. The amount of heat, always remember, is delta Q, is delta U plus delta W. So this is an ideal gas. U is determined by U is equal to CV times delta U is CV times delta T, and therefore isothermal process delta Q and delta W are equal, and delta W is what you calculate. So W is what is being calculated to get Q1 and Q2. So this is now where we were was that there was one final step to be taken, that one had to show that this ratio and this V2 over V1 and V3 over V4 are the same. So one had to worry about the processes going on over here. It's an adiabatic process. So it is PV to the power gamma equal to constant. Now, if we use the ideal gas equation of state, which is P equal to RT over V, then this is the same as writing T times V to the power RT over V. So T times V to the power gamma equal to constant, which in turn can be used in another way that the different manifestations of this constancy, PV to the power gamma constant, TV to the power gamma minus 1 constant. We now also need for good measure, express it in terms of P and T. If I do that, then V is equal to P divided by T. P divided by T over here. So this is T. V is PV is RT. So it is T divided by P to the power gamma minus 1, which is equal to T to the power gamma and divided by P to the power gamma minus 1. So that's another way of writing it, that T to the power gamma, so it is PV to the power gamma constant, T times V to the power gamma minus 1 constant, or in terms of temperature and pressure, it is T to the power gamma divided by P to the power gamma minus 1. So that's constant. So these three ways of getting this done. Expressing this adiabatic condition. So it's the adiabatic condition which we can write in different ways, and it's in terms of PV so all right. And what you have to do is calculate. So all right, it is V2 over V1 and V3 over V4. So that is what we have to make sure. So let's make use of this, that it is T times V to the power gamma minus 1. So let's look at for the adiabatic process, that is from here to here. This is T1 to T2. The volume goes from V2 to V3. So T1 V2 to the power gamma minus 1 is T2, and then it is V3 to the power gamma minus 1. Come here, it is T2. At this point to here is another adiabat over here. Temperature is T2 and the volume over here is V4. So it is V4 to the power gamma minus 1, and that is equal to once again this T1, and it is back T1 over here, and the volume is V1, so it is V1 to the power gamma minus 1. So this is the path 2-3, adiabatic path 2-3. This is the adiabatic path 4-1, and now you divide out. So V2 over V1 to the power gamma minus 1 is therefore dividing V2 over V1 is equal to V3 over V4. So now you see that Q1 is this quantity over here, Q2 is this quantity over here, but this is the same as V2 over V1. So RT, this amount of heat rejected is RT2 times log of V2 over V1. So that's and therefore when I write 1 minus Q2 over Q1, Q2 over Q1 is RT2 times this divided by that. but this quantity is the same as this quantity. So this is equal to 1 minus T2 over T1. So that's the efficiency of the Carnot engine. So 1 minus T2 over T1, the efficiency of the all Carnot engines are equal regardless of substance. Therefore, you calculate it with the ideal gas and you have the general result that independent of the working substance, the Carnot engine has efficiency which is 1 minus T2 over T1 determined by the temperatures of the two baths that it connects. So that is the Carnot engine efficiency, which is important result. And now the thing is that one having got this, we need to establish the other important general result in this business, that of all between all engines operating between these temperatures T1 and T2, Carnot engine is the most efficient. So here we are. What one does to do establish this is, here is this temperature bath T1, here is T2, and what you do is run an engine, normal, not a reversible engine, which is which we will call just a engine and write E. So it draws Q1 amount of heat, does a certain amount of work W, and rejects a amount of heat Q2 to this sink over here. And then you run a Carnot engine in reverse. That is, in all these you will find there are probably more results about Carnot engines if one looks around. The two important ones which will certainly which we are covering are certainly the most important, but there can be I'm sure if you look up engineering texts in particular, you will find very many different ways of doing this. So we have really not looked in, we are not going to look into that. But the one thing which I can point out, that anything where you have to compare a normal engine and a Carnot engine, and one is required to show something or other, that Carnot engine can do this better, or Carnot engine does this in some thing or other, you can be sure that the proof runs by considering a cycle where the engine runs in the normal way, extracts heat from a high temperature reservoir and rejects some to the low temperature reservoir and does some work. The Carnot always works in reverse. So that's the specialty of the Carnot engine. And therefore, whenever somebody has to says that there is a result which compares a normal engine to a Carnot engine, you can be reasonably sure that the proof of that result will involve the normal engine running in the only way it is allowed to run, and the Carnot runs in reverse. I mean, that's, I think, a reasonably general statement about how to look at problems involving engines and a Carnot engine, a comparison problem. So anyway, I mean, that's some practical statement which is probably reasonably correct. I can't be sure that it's absolutely correct. So anyway, and now there is a Carnot engine. So what does the Carnot engine do? The Carnot engine takes a certain amount of heat. I'm going to run it, as I said, runs in reverse. Takes in Q2 prime from over here, and then it takes in a certain amount of work, W prime from over here, and deposits to this high temperature reservoir. This is at T2, that's at T1, and to this high temperature reservoir, it delivers amount of heat, which is W prime plus Q2 prime equal to Q1 prime. So between T1 and T2, we are considering a process where it is a forward cycle for the engine and a reverse cycle for the Carnot engine. So there is Carnot and the normal. All right. So now what? Now the argument says that I have to show that the Carnot engine's efficiency is greater. So the way one does this is consider N1 cycles of E and N2 cycles of C, that is reverse, C running in reverse. So you consider N1 cycles of E and so all right, how much heat? So question is heat leaving T1. Heat leaving T1 is N1 Q1 minus N2 Q1 prime. So Q1 prime is the amount of heat which is being deposited to T1. So heat leaving T1 is N1 Q1 minus N2 Q2, Q1 prime. Work done equals, there is N1W, that's the amount of N1W, which is the work being done, and the work which is being taken in, which is minus, is N2W prime. And then there is heat deposited in T2 is equal to, so I have N1 Q2 over here. So amount of heat deposited is N1 Q2, and what I have taken out is this, which is N2 Q2 prime. So that is the after. So I have run N1 cycles of epsilon and of engine, and N2 cycles of the Carnot in reverse, and the total process over here, this process of running it. So now I'm going to consider the situation where no heat, net heat leaving T1 is 0. So I'm going to consider heat leaving T1 equal to 0. So I have N1 Q1 is equal to N2 Q1 prime. So, all right, and over here also Q1 minus Q2 is equal to W, just as over there. I mean, this. So the work done is the N1W minus N2W prime, and the N1 and N2 are now related by this quantity over here. And let me put in the N1 and the W and W prime in terms of the heat involved. So I'm going to write this work done, this quantity over here. So the work done, I'm going to write as N1 into W, which is Q1 minus Q2. So this work done is what is being written, minus N2 and W prime, which is my Q1 prime minus Q2 prime. So Q1 prime minus Q2 prime. So that is my setup, and of the work done. N1 Q1 minus N1 Q2 minus N2 Q1 prime plus N2 Q2 prime. And what I have done is that I have this condition that I have set is that N1 I have adjusted the number of cycles so that N1Q1 is equal to N2 Q1 prime. So N1Q1 over here cancels the N2Q1 prime over here. So yeah. So this work done, which I was after, is now N2. So work done W becomes equal to N2 Q2 prime minus N1 Q2. So W, the work done, has become N2 Q2 prime minus N1 Q2. Now notice the heat deposited in T2 is N1 Q2 minus N2 Q2 prime. Therefore, heat leaving T2 is equal to N2 Q2 prime minus N1 Q2. So that is the heat leaving Q2. So now what has happened? What has happened is that I have adjusted things that there is nothing happening at T1. The net heat leaving T1 is equal to 0. That is the condition. I have taken the number of cycles in a manner that that quantity is equal to 0. So nothing is happening at this level. What is happening at T2, the bath at constant temperature T2, there is a certain amount of heat, N2 Q2 prime minus N1 Q2, which is leaving, which is being drawn from the temperature T2. And how much work is getting done? The identical amount, N2 Q2 prime minus N1 Q2. So what we have engineered is that we have managed to extract heat from a reservoir and converted it into completely into work, and therefore that cannot happen, and that cannot happen. So it is not possible for you to have an engine whose efficiency is greater than the Carnot engine. So between of all engines running between temperatures T2 and T1, the Carnot engine has the maximum efficiency. So that's the theorem which is vital, and that essentially, I mean, does the sort of finishes the conceptual part of this second law. The primary business with the second law lies in the fact that which let me sort of this is actually a very interesting exercise in sort of arguments, logical arguments, and therefore the second law is discussion is actually quite not so easy and also quite interesting. So we started out saying that there are two formulations. So that's already very somewhat funny. So there is the Kelvin business.
So I have a question.
Yeah.
Yes, sir. So here we had taken like N1 Carnot engines and N2 reverse Carnot engines. So
Yeah.
like how does this actually like prove that Carnot engine has the maximum efficiency? How does it imply that?
Sure. So, all right. So, the point is that if the right, I should have clarified that. So here is a situation where I have taken the normal engine, which has a certain efficiency, which is capable of running in the forward direction, and its efficiency is given by 1 minus Q1 over Q2. I have taken a Carnot engine which runs in the reverse direction, and the efficiency of this, it should have been Q2 over Q1. So the efficiency of this engine, which is E, is this. The efficiency of the Carnot engine, which is 1 minus Q2 prime over Q1 prime. So that is the efficiency of the, so if you want this thing to, what you want to show is that the Q2 prime over Q1 prime has to be smaller than, so Q2 prime minus Q1 prime has to be smaller than Q1 over Q2. So that is what you were interested in showing, and what you have demonstrated, that it is this Q2 prime over, let's see, where were we? Here, this heat deposited and this heat leaving Q2. So we established that this W, which is N2 Q2 prime minus N1 Q2, has to be, the sign of it is, it's the amount of heat which is leaving T2 is this quantity over here, and that cannot be positive. So because that would violate the second law, and so it is N2 Q2 prime has to be less than N1 Q2. So N2, So which is N2Q2 prime is N1 less than N1Q2. So Q2 prime over Q2 is less than N1 by N2, which is equal to N1 by N2, which is equal to Q1 prime divided by Q1. So Q2 prime over Q1 prime. So Q2 prime over Q1 prime is less than Q2 over Q1. Therefore, 1 minus Q2 prime. Therefore, eta C is greater than eta. Got it? Understood?
Yes.
Yeah. So that's the rest of the. Once you have demonstrated that this is done, I mean that's the rest of the.
Sir, what was the motivation behind doing N1 cycles and N2 cycles of C?
What?
What was the motivation behind doing that N1 cycles of E and N2 cycles of C? Means, does the number of cycle can affect the efficiency?
I mean, the number of cycles were taken just as a device for getting at the proof. The final answer has nothing to do with the number of cycles, right? I mean, I can always, given any Q1 and Q2, I can always choose an integer which is like a set of integers which are large enough so that this relation between
I can't see you. We can't see the board either.
So and N1 and Q1, so I can always take large enough integers to ensure that given any Q1 and Q1 prime, this relation holds. And therefore, every time you give me a Q1 and Q1 prime, I can give you a proof of this. That's
Camera has turned off.
Sir, then if N1 and N2 had been equal, then we would have got equal number, means efficiency of the engine and carbon engine would have been equal.
The whole idea is that no, I mean, if N1 and N2 are equal, then it is you don't even, it's Q1 equal to Q1, everything is the same. So, I mean, you have essentially, you can run the other in reverse as well. So, I mean, but that's, one wouldn't be running into, it would have to be, if I have a engine which is a different, it's a question of finding, if I just set that Q1 equal to Q1 prime, and you want to do a proof with that argument, there is a way of doing that also. This is not the only way of getting the thing done. You can, I mean, maybe you can do it as an exercise that I don't need to take, go through this route of taking N1 cycles of this and N2 cycles of that and adjusting my N1 and N2 in a different manner. You can just consider one cycle. You can consider one cycle of this with Q1 and Q2 over here, and a Q1 prime and a Q2 prime over here, and a W and W prime. Set yourself the fact, put yourself in a situation where there has to be no heat deposited over here, and then go try and set up the logic which would show that if that is so, then there would be a violation of the second law. So, or you can do it that way. The argument is a little tricky over there, but it can be done. So you can just try it out with a single engine. The same kind, the proof is now going to be a little difficult, a little more logic. Over here, the advantage of taking N1 and N2 is that the logic part of it is taken out. You just do some calculation and they're at the end of it. You can do it with a single stroke and a single operation, one cycle, and then you have to use a little bit of logic. You can still get there. Yeah.
Excuse me, sir. So the camera has turned off. We cannot see the board.
Huh?
So the camera has turned
Sir,
off.
the
We
camera
cannot see
has
the board.
turned off. We cannot see the board.
You can't see the board.
No, sir. No
No, sir.
video is on. The camera is turned off.
Mm-hmm. I'll rotate this. Tell me when you can.
Yes, sir.
Can you see it?
No, 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 sir.
No. Can you see now?
No, sir,
No,
not
sir.
yet.
No?
So the camera is off actually. We cannot see any video.
Like we cannot see you, not the board. Just black screen.
See what can be.
Yes, sir, the video is on.
Right. So what you may not have been able to see, the answering the question that what happens if N1 is equal to N2. Well, what happens is that you can do the thing for a single by going through this proof over here. The whole idea is that you can do some algebra, and at the end of the day, you are there. If I want to say that I will use only one cycle and try to establish this, it would have to be entirely a question of logic, which you can set up and do for yourself. That as I take this cycle and one reverse cycle which puts in some Q1 prime over here, and now try to argue that if Q1 and Q1 prime were equal, what would happen to the W and the Q2s and the W? It can't be that all the W will be taken up by W prime, taken up as W prime. There has to be, if I set these two equal, there would have to be some difference over here, which in turn would be related to the difference here. And that would once again allow you to establish that the Carnot, which is running in reverse, has a greater efficiency. Sure, you can do this with one, but with more logic statements than just some manipulations. Sure.
So the Carnot engine is so special because of the way it runs. Isothermal, adiabatic, and then isothermal.
What happened?
So the Carnot engine is so much special, means it has the highest efficiency among all of the engines. Is it because the way it runs?
What is special?
Means the highest efficiency it has among the other engines that could be produced.
No, এটা বুঝতে পারছি না কি কোন কাকে মানে স্পেশাল একটু আরেকবার বলো, মানে আসলে অডিওটা এতটা ইয়েতে আসে না, যে ভেঙে যে একটু অসুবিধা। সো আরেকবার বল।
হ্যাঁ 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 স্যার, আমি বলছি যে কার্নো ইঞ্জিনটা খুবই স্পেশাল, কারণ কি সেটা বাকি ইঞ্জিনের থেকে সব থেকে বেশি এফিসিয়েন্ট। তো এটা কি তার যে প্রসেসে রান করে, মানে আইসোথার্মাল, অ্যাডিয়াবেটিক, আবার আইসোথার্মাল এন্ড দেন অ্যাডিয়াবেটিক, এই জন্য কি?
All right. Yes, right. I see. What you are asking is that why no, it is not so much. It is a question of being able to do everything reversibly. When a Carnot engine is more efficient, see, this reversible essentially means that in effect that there is no dissipation really going on anywhere. I mean, that is the reversibility has automatically sort of implies that if there was some dissipation, like, I mean, some viscous action or current flowing and losing the heat being radiated away, that kind of dissipate the resistance. I mean, resistance generating heat when, so those are the kind of things which in this reversible engine you are completely ignoring. So just as, I mean, if I stir up liquid and create heat inside it, there wouldn't be, that's a situation which I would not be able to reverse. There is dissipation and that is it. I mean, reversible is a sort of idealization where you can sort of go, let's say, backward in and recreate all the steps. It is the reversibility of the Carnot engine that what makes it special. It is not the as so much as the having adiabats and isothermals as the process. Only the processes are 2 adiabats and 2 isothermals, but it is more a question of being of setting up a reversible process and thereby getting this done. Point, of course, what you can ask is that, all right, can I set up a reversible process with without considering 2 adiabats and 2 isotherms? Well, it is what we will be, I mean, whenever one is calculating these things, it is, there is a question of every time there is a quasi-static question, all calculations which one does in practice has this quasi-static feature. The reversibility is the reversibility is stronger than the quasi-static. So with the Carnot cycle, the reversibility is what makes it special in the sense that you can actually run things. I mean, it is not so much as a question of the adiabat, but whatever you do, you can reverse it. That is the feature which makes the efficiency the maximum, and not really the nature of the process, whether it is isothermal or adiabatics and isothermals, or isobars and adiabatics and so on. So it is, I guess, a question of, to answer your question, it is the reversibility is a much stronger criterion than what kind of path adiabat, and that it is the reversibility that you can actually run it in reverse. That is the so somewhere along the line, something which is reversible can be pictured as something which has no dissipation. That is what I think makes it most efficient. All right. So, but I mean, maybe the next couple, what I wanted to do next makes the point in some form or another, that I want to go away from the Carnot engine, from this particular kind of car, and talk about more sort of practical engines. So practical engines, and I get, all right, I mean, to make it why this reversible, irreversible, I think the next lecture that I would like to, the material I want to cover in the next lecture should be able to drive home the point in a more interesting manner. All right. So I want to talk about actually practical cycles for the rest of the class today. That things which are within your ability to calculate easily, and which also have bearing on what the have some bearing on real life. So real life, the most popular business should be, one of the more popular things is a car engine. So the car engine, which the standard model that one uses for the car engine, which is more properly the gasoline engine in a way. So once again, PV diagram, and the thing which you will notice that almost everybody uses two adiabats. That seems to be a common feature. There must be. So you start, let's say, over here, and what you do is you compress. You press the volume of this where the mixing of gases would take place. So you essentially compress the gas, and you compress it adiabatically. So you start from here. So you start here, and there is a compression. So let's say if I call it A, you compress and you go to B. So this is a adiabatic compression. Before, I mean, there is always sort of in these car engines, state where, I mean, you essentially, the volume was very low, and there is a stage where you sort of initialization where the air is allowed to expand, and then you get going on it. So there is some always a hidden mechanism in the beginning of the cycle itself, where a very small amount of air is allowed to come into the chamber and occupy a small volume of air is allowed to come into the chamber and occupy a much larger volume, and you start action from there. I mean, the engine cycle. So the engine cycle compresses it, and this compression is an adiabatic compression. Now, the adiabatic compression over here means that all right, I have a smaller volume, and the point is I have to heat it up. So the next step is heating it up. So you heat it up through a process over here, which is isochoric. So you keep the volume constant. So there is an isochoric process. The volume is fixed, and you heat up the thing, and its pressure increases. So this is where you supply heat, the Q1 coming in over there heating up the gas, and the heat does work. So it is the heat which does work for you. And then you come up to this point C over here. That is the end, and then you let the Q1 heats up the system, gives you the energy to do the work. The work comes at this stage where you allow the gas to expand and do the work. So your gas expands and does the work. So you put in heat over here. The heat changes the temperature. It changes the temperature change from here to here as well. But here is the rapid rise in temperature because you have put in heat over here. The rapid rise in temperature, this is the spark, essentially the ignition actually, which ignition process going on going on over here. And then the pushing out, the system does work by pushing out the gas, which expands in volume, and you come over here and then bring it back to this point once again, and you do that at a constant volume. So you allow the relaxation over here, heat taken in over here, heat rejected over here. So this is where the heat gets rejected to the system, and you relax back to the original system. So this is this is a idealized car cycle, and then actually you let it go back over here, and then things start. But this part is generally, you don't see it as a part of the cycle, because essentially you start from here, and then, I mean, while, as I said, you actually start from a more dead state, and then you, at the end of the day, you also return to the dead state. So these are essentially canceling each other out. And the cycle that you see in the car engine, the idealized cycle, is this over here, which is generally known by known as the Otto cycle. So that's the Otto cycle that you have over there. There is a variation. So this is the car engine. A variation of this is a cycle where this isochoric is replaced by a isobaric. So you come up over here. So you start with your, this is 1. So here is pressure volume. You go through an adiabatic compression. So here is the adiabatic compression here. So that's the adiabatic compression. And then at constant pressure, you let it expand. So it expands at constant pressure. That is where you get the work done. So constant pressure and execution, that is where the adiabatic compression over here has raised the temperature, and then there is this question of getting work out of the system, and then adiabatic expansion once again. So here is the adiabatic expansion, which relaxes, and there is work done over here as well, and it is the you are picking up a big part from over here. Then there is the adiabatic compression, which also gets you, and then finally you come back over here. This is a variant on this cycle over here, and while this is used in that is this prototype of a car engine. What this is a this can be used in two different ways. It can be that it can be used as an open system, that is, the work is done by air which you suck in. So air sucked in, that is what you use for doing the work, and then you let the air out. So the cycle begins with sucking in air and then letting the air out when in this expansion stage over here. So it is not recycling, it is just sort of, the operation is being done repeatedly, but it is air from outside sucked in and air outlet over here. In this form, it is a jet engine. And if you use it in the form over here, where it is all a closed system. So if you use it as a closed system running this cycle over here, then it is this turbine, gas turbine operation. So this is in the closed form. So between these two, this is the Otto cycle, this is the Brayton cycle. Between these, there are numerous cycles that one actually sees. As for my choice, the two cycles which you should have an idea about this basic car cycle over here, which is the Otto cycle, and the basic jet engine mechanism or the turbine, which is this Brayton cycle over here. In my way of looking at things, these are all personal. This is, I would essentially think that if you, so all right, one has to look, what is one supposed to look at? One is supposed to look at efficiency. So efficiency now, the temperature is T1 over here, and then you compress it, and it becomes a T2 over here. And then there is this question of putting in heat over here. So temperature changes once again, and it becomes T4 over here. So look at the difference from the Carnot business that we did, where it was taking in isothermal, adiabatic, and isothermal adiabatic. The adiabats are always there. Notice that the adiabats seem, because it's there is a work done component over here. So the work done component means pushing out, and pushing out is when it is done rapidly, it has to be adiabatic kind. So things have to happen fast in these mechanisms, and therefore, and there has to be some pushing out, and therefore the adiabatic expansion. And if there is a adiabatic expansion, I also need to compress adiabatically. So the adiabatic parts are really similar. I mean, that is similar, meaning that they always exist. The two differ, these two cycles, which are used in very different circumstances. It is the connection between the adiabatic paths which are different. So the two adiabats connected over there by vertical lines, the two adiabats connected over here by horizontal lines, and therefore they sort of, at least in my way of represent the two extremes of the engine varieties. The adiabats would always be there, but how you connect the adiabats, these to me seem to be the two extremes of connecting adiabats. So, all right, So connecting adiabats, as we said at the beginning, have this property that PV to the power gamma is a constant, and similarly is not the same constant, but a constant is V to the power. So this becomes RT over V to the power gamma minus 1 times T. And then the other constant is this your pressure when it is T P to the power, or rather T to the power gamma by P to the power gamma minus 1. So these three different forms. And now if I look at this over here, the efficiency is always 1 minus heat in heat in by heat out, which is 1 minus Q2. The two adabats are out of the picture, and it is what you are drawing in is Q1, and what you are leaving is T1, this part over here. Q2 is, this is your Q2 over here, and that is going to be specific heat times T4 minus T1 over here. And so it is T4 minus T1 over there, and then it is T3. So puts heat into the system, and it is going to get hotter. So it has to be T3 minus T2. Get heat out of the system, has to cool down. So it is T4 minus T1. And so it is 1 minus T4 minus T1 divided by T3 minus T2. What you want to do is write this in these cases, the efficiency. So what is my target? The target is to write the answer in terms of T1 and T2. So this T1, because that is the most important set of temperatures in a way. It was the ambient temperature over here, where and then you compressed it to essentially this point over here, which allows you now to get going. So going from here to here, this adiabatic path, T1 over T2, that is a important, I mean, those are, you could have expressed, all right. What I mean to say, what I want to say is, this is the expression, and you can go ahead and eliminate any two and write it in terms of the remaining two. So, all right, the question is, what do I eliminate? So the preference is to, I mean, T1 is a temperature which you are very easy, it is the ambient temperature, and therefore it is best to keep it. And if I keep T1, then the automatic choice for this is to other one is to go with a T2, because that is the result of the compression, the cycle. So you want the answer in terms of T1 and T2. So if I want to do that now, it is a question of writing. The adiabats tell you that this was the adiabat over here, and therefore it is this was V2 over here, and it is V1 over here. So it is V2 times T1 to the power, it is VT1, what V is V2. T1, V2 to the power gamma minus 1. This is equal to T2, and that is at V1 to the power gamma minus 1. So T1 over T2 is V2. So that's that. Then there is the other adiabatic path over here. So it is T3, and this is a volume V1. So V1 over to the power gamma minus 1 is equal to, over here, it is the temperature is T4, and the volume is V2 to the power gamma minus 1. So here we are. So T1 over T2. So if I look at T1 divided by T2, so T1 or rather T3, sorry, T1 by T3 is equal to T2 T4. So on this side, I have to take T4. So if I take T4, no. So I take T1 V2 gamma minus 1 is T3 divided by this. So V2 over V1 minus gamma. So V2, sorry, I wanted to come from here, right? V2 over V1 T1 minus, sorry, should have done it with this. So T1 by T2 is V1 over V2 to the power gamma minus 1, and V2 over V1, this is T1 has V1 in the in the numerator. So over here it is T4, which has, this is equal to T4 by T3, right? T1 is the lower temperature, T2 is the higher, T4 is the higher temperature, T4 is the lower temperature. Here this is an adiabat over here. So this is T3 and T3, and I just want to get the right. T3 is at a lower volume, and therefore the T4 has to be lower than T3. So T4, what did I write? So T2 over T1, T4 over T3 has to be a small, and it has to cool down, adiabatically expanded. So it has cooled down. T4 by T3 is V1 by V2. And it is T1, what happened? What did I do? So it is T1 V2 to the power gamma minus 1. That is equal to T2 V1 to the power gamma minus 1. And V1 is smaller, and therefore T2 is larger. So that's correct. Now it is T3 and over here. So I have heated it up, and T3 is bigger. So T3 is bigger and the volume is V1. And here is the adiabatic process. So it is T4, which is V2. V2 is smaller over here. So T3, V2 is larger. So T3 is greater than T4. So T2 here is greater than T1. And it is this is consistent with having T4. T4 over T4 is over here. T4 greater than T3, right? So T2 greater than T1 and T4 greater than, so this should have been correct. So it is T2 over T1, which is T4 over T3. And now I can go ahead, and here is my T4 over T1. I can take out T1 over...
I think that would be T1 by T2.
Yes, sir. I also think T1 by T2 equals to T4 by T3. What? T1 by T2, sir. I think it should be T1 by T2 equals to
T1 by T2. T1 is the lower temperature. T1 by T2. So that is the higher this is lower temperature, that is higher temperature. And T4 is the lower temperature and T3 is the higher temperature, right? So T1 by T2 equal to the, thank you. So T1 by T2 equals to T4 by T3. And now I want to write this in terms of, I take out a T1. So I take out all right, I guess that's done. I'm almost a bit, I'll leave the other for you. So this is equal to 1 minus, and it is T1 by T2 into 1 minus T4 over T1 by 1 minus T3 over T2. But T4 over T1 is T3 over T2. So this cancels, and therefore the efficiency of the car engine is 1 minus T1 by T2. So the engine over here, this car engine over here has the efficiency of 1 minus T1 by T2. So what's the, how much does it come to? T1 is room temperature. So T1 is like 300 degree Kelvin. The pushing in and igniting the ignition takes you up to a temperature which is roughly 600 degree Kelvin. So the eta which a car engine should have is about 50%. So the car engine is the idealized car engine which we have analyzed over here is roughly should be about 50%. Reality is that the ratio, that the efficiency is about 30%. So this is where this is the approximation. This is the result of the you are using reversible processes. You are using a reversible process to set up an ideal engine, and the ideal engine has the with realistic figures of temperature gives an efficiency of 50%. Reality is that the efficiency is about 30%. I would, request you as a sort of assignment, work out the thing over here. It is, as you can see, very similar to what we did, except that the lines are, the vertical lines over there are replaced by two flat lines over here. And you will get a similar kind of answer for the efficiency for the Brayton cycle. It's worth your while to work it out, because after all, it is it models the other extreme from a car engine to a jet engine. So you have a whole spectrum, and the calculations are more or less similar. So it's interesting. So you might, I would recommend that you work it out or look it up in textbooks.
Is it same for the electric engines?
What?
Electric engines, the electric motors that drive the cars. Electric cars or electric engines that runs on electricity, not on the conventional fuels.
কিছু বুঝতে পারছি না কি বললে।
He is asking that if it is same for the electric engines, like electric motors.
Electric motor. Acha. All right. That is, if I replace the car from a gasoline engine to an electric engine.
Yes, sir.
I don't think the efficiency changes very much. And I don't think I can't be very sure. It is not so much as the efficiency as such is, because the strokes remain the same. You still have a cycle which is going on of this kind, and therefore the process is not very different. But the issue, the only reason why one wants the electric car is the question of the emissions are not so deadly. So that is really the, it's more an environment issue than a question of efficiency of this. Yeah, right. But it is the 30. So Brayton, please try and work it out. And next class, I will actually show you a model where we can, I mean, what should be the answer if I'm dealing with a real life engine? So that's something which normally you would not come across, but it is something which, courtesy a couple of essentially college teachers in the US who worked out this absolutely fantastic argument on how to get a real life answer for the efficiency of a real engine. So we'll have a look at that next time. And go ahead.
Thank you, sir.
Okay.
Thank you, sir.
Uh,
Thank you, sir.